Remember these? These black holes are so compact and so far away that in order to get these pictures, we needed a telescope the size of the Earth. The resulting images were among the sharpest views of the cosmos ever obtained. Despite them being groundbreaking, some people were disappointed, calling the images blurry. I personally was super excited that we finally got to see what black holes look like up close. I just wish we could go a little deeper. Well, my wish may be about to come true. Astronomers just announced that they succeeded in making the highest resolution observations ever obtained from the surface of the Earth. But if we already had a telescope the size of the Earth, how is that even possible? Let's take a step back. These images, taken by the Event Horizon Telescope, or EHT for short, show the biggest black holes in the sky. But they are still extremely compact, only about the size of a donut on the Moon as seen from Earth. And what we're seeing here are not actually the black holes themselves, but the material that is caught in a death spiral around them. And we're not observing visible light that we can see with our eyes, but in a part of the electromagnetic spectrum called the millimeter, more precisely at 1.3 millimeters. To detect millimeter waves, we need dish antennas. The larger these dishes, the smaller the patch of sky we observe, and the finer the level of detail we can see. We call the level of detail we can just about recognize angular resolution. So if we want a more detailed image, the obvious solution is just to build bigger and bigger dishes. The problem is, at some point, this costs too much, requires too many materials, and just becomes physically impossible. Instead of building one impossibly colossal single telescope, we can use a special technique called interferometry to construct a giant virtual telescope consisting of several individual telescopes. The combined observation will have an angular resolution or image detail the same as one giant telescope with a diameter corresponding to the biggest distance between any two telescopes. Interferometry is also how ALMA, in which ESO is a partner, works. ALMA consists of 66 individual antennas spread across the Chasing plain in the northern Chilean Atacama Desert, and it can make extremely detailed images of our cosmos. ALMA can reach angular resolutions down to 5 milliarc seconds, which is the same as seeing a 10-meter-long bus on the Moon. While ALMA was already a game changer for millimeter observations, the EHT went a step further by using very long baseline interferometry, or VLBI for short. VLBI is a little bit like interferometry on steroids. Rather than just tens of kilometers, the individual telescopes can be spaced hundreds or even thousands of kilometers apart. The EHT combines simultaneous observations from telescopes around the world, including ALMA. And it then used sophisticated computer processing to obtain these iconic images. In case you're wondering why not all modern telescopes are interferometers, well, this technique comes with some serious caveats. In particular, the data has some gaps. This is a bit like a sentence where letters or even whole words are missing. In order to reconstruct the sentence, it helps to have some idea of the content beforehand. The same is true for interferometry, in particular VLBI, where the spatial gaps in the data can be extremely large. Image reconstruction in interferometry is an extremely complex process, and it would take too long to explain it here. But if you would like a separate video on this, please let us know in the comments, and we'll be happy to oblige. Given that the EHT is pretty much the size of our planet, there doesn't seem to be much room for improvement in terms of telescope diameter, bar going to space. So does that mean these are the sharpest images of black holes we'll ever get? In fact, the telescope diameter, or the maximum separation between individual telescopes in interferometry, is not the whole story. To get a sharper image, which means a smaller angular resolution, you can also observe at shorter wavelengths. So basically, you get a sharper image if you have a big telescope or small wavelengths. To illustrate this fact, you can check out these images of a planet-forming disk taken with ALMA. They were taken at slightly different wavelengths, and you can see that the one taken at shorter wavelengths is clearly sharper, which means that we can distinguish more detail. So if shorter wavelengths mean sharper images, why does the EHT observe in the millimeter rather than, say, in visible light? The answer lies in how VLBI works. Radio or millimeter waves are stable and coherent over large distances, unlike visible light. And this means that even if we have our telescopes on different continents, we can be sure that we're recording the same wave. Also, since the telescopes are not physically connected, in order to combine the data, we need to first record the individual data streams and clock them accurately. For visible light, this is simply not possible because our clocks are not accurate enough. So the trick is to find the sweet spot, the shortest possible wavelength where digitization of the signal is still possible. Currently, this lies in the sub-millimeter regime, so just shortward of the millimeter. This is why it's so exciting that they finally presented their groundbreaking observations at 0.87 millimeters. These are the highest angular resolution observations ever taken from the ground. The new EHT results constituted test observations, which means that we're not sharing any images just yet. But the team managed to achieve an impressive angular resolution of 19 micro-arc seconds. While that might not sound like much of an improvement on the 20 micro-arc seconds they had previously, it does serve as a proof of concept, showing us that we can push to shorter wavelengths and obtain even sharper images in the future. The thing is that during these test observations, the weather wasn't great at all of the sites, meaning that not all telescopes' data could be used. The EHT team estimate that with better observing conditions, they will be able to make images with an angular resolution 50% better than was possible before. And more detailed images means better science. In the future, we hope to be able to measure the U-shaped orbit of light around the black hole, and we hope to be able to see the launching point of their massive jets. We also hope to be able to test in multiple ways the predictions of general relativity. We may even be able to obtain images of other, smaller, fainter black holes beyond the two we already have. This is just the beginning.